All right, everyone. It is now 2:30. Welcome back to another Comp 290 lecture. This is lecture 8. Before we get started, I'm going to share a few announcements. So the first one is, as you know, last week we talked a little bit about the final project, and we showed the document for the final project on. Oh, it's working now. Okay. We showed the doc about the final project instructions last week, and we showed the different parts. There will be soon coming out, probably today, hopefully, an interest form. That will be an Airtable form similar to the one that you submitted for the survey and also in the beginning of the class. This is just to gauge your interest in a potential track that you may be interested in, or the type of project that you might be considering. You'll have a week to submit this, and it's not binding. So if you choose to, if you choose a specific track in this form, but then later in a few weeks you want to change it, that is okay. This is mainly, again, for our planning purposes, so that we have a general idea of where everyone is at. In addition, because this question did come up, and I'll see if I can pull it up. One question that we did have last week was involving working with a partner. So if you want to work on a partner with this, or if you're planning on working with somebody and actually developing this final project later, you are welcome to. And so we modified the instructions a little bit. So basically, in order to make this such that everyone is still doing kind of an equal amount of work, we're changing a few things. So one, for the project outline, we are going to increase the word count by a little bit. Everyone should complete their own getting started tutorial and submit it. So if you're in a pair of two, the reason why we're doing this is we do not want just one person doing, for example, if you're in the iOS one person doing all of the actual coding work and everyone else doing the writing. And to prevent that, we're going to have everyone submit their own getting started tutorial piece. That allows everyone to have the opportunity to get involved and to have a deep dive into the topics that they're interested in. And then we're adding one extra, so everyone should just add one extra goal and one extra task into the action plan section. So if you're interested in working in a team, you can also specify that in the form that'll go out, and you can put the name of your partner there. Any questions here? All right. So another thing is that there will be, probably next week, there will be a link to a GitHub Classroom assignment. And this GitHub Classroom assignment will actually be a repository that contains all of the pieces, including the templates, that you will need to complete the final project. And you'll have access to this for the remainder of the semester. So I'm going to see if I can actually pull this up. That way I can very briefly show what the format of this would be. So that would be, I assume, Comp 290. And when you all submit this, you'll have an actual link to this. You won't have to follow this process that I'm doing here. But there will be a template that looks similar to this. So this is the final project template, and you'll have the three different pieces of the project, which are the three different headers. There are folders for those. So you can see there's a proposal, action plan, and getting started. And in this README file here, which is all written in Markdown, you will see that we explain where the different pieces of the project will go, and there will also be a getting started section of how you can download this repository to your computer, and also another summary for the grading criteria. If you click on any of these, so you'll be starting out with the proposal, you'll see that there is an outline file, and this outline is the one that you can modify to answer all of the questions. So this is just looking a little bit ahead. There's nothing due here right now. This is just to kind of, if you're wondering, or if you wanted to start early for whatever reason, you're wondering where to find the templates or trying to figure out how to actually package everything and how you'd submit it, it will be in this repository. And we'll send a link out for that. Any questions here? All right. So that is all I have for the final project section. Lastly, their Hack and See registration is still open. We've shown the picture a few times in the last few weeks, but again, still open. So if you're interested, feel free to look that up and sign up. And then the last thing here is just for our own bookkeeping purposes. How many people are planning to, or I guess either have something or somewhere that they're going next week on Wednesday? Is there anyone who will not be here? Because I know that there is fall break happening. All right. So I think looking ahead a little bit, we're going to, we'll probably send some information out about that class soon. If we were to go async, for example, on that day, and which I think would help a lot of you because that might be your last class of the day before break, there will be some extra information sent out that that will help just more info about the final project and how to look up different resources, because that's what the plan was going to be for that day. So you can see, we'll send that out in an announcement later today. So keep that in mind for scheduling purposes. Okay. And so I think with that, I can hand it off to Noah to talk about the internet.
All right. Thanks, Ajay. Yeah. So today, if you guys came in, didn't see the title slide, we'll be going over networking and at a lower level the internet, and really dialing in on that. And this was actually sort of a recent change by Ajay and I. We sort of realized, like, oh, this is kind of really important for a lot of subjects, not just software engineering, although very prevalent there, but really anything you get into where you're using more than one computer in the future, the internet and networking is going to play a big role. So that's sort of the motivation behind this one today, and we'll be focusing specifically on the internet towards the tail end. But just to get started, right, this is a really basic question. You guys probably have some sort of working definition. Can anyone just tell me right now, in your mind, what is the internet? When someone says that, how would you define it if someone asks you this question? Yeah. A bunch of hardware hooked up to each other. Okay, do you want to expand on that, or?
I mean, most of the internet is just massive server farms connected by massive wires, even under the sea, and eventually gets to us personal end users through wireless connection through routers.
Nice. Yeah, good. That's a pretty comprehensive answer. Yeah, so a lot of server farms hooked up, everything physically networked together by cables. That's a good starting point. So let's dig into that some. This is just the word itself, internet, comes from interconnected network. It actually goes back a long time, which we'll dive into here in a second. But yeah, so it just refers to the connection between all the computers in the world. So well put by Vincent there. A lot of just physically connected hardware all around the world. And a network at its most fundamental core is just a connection of two or more computers. If you just connect up, even like at my house, if I connected up a few computers together, that would be a network, right? It's not necessarily the internet. It's not the interconnection of all the computers in the world, but it's a network that I have locally. And you'll see this everywhere. I mean, the school has its own network. Most businesses have their own network. Your home, you have a home network. And then that itself is connected to the internet. And so the internet, it's often synonymous with the World Wide Web, WWW, although they're not the same thing. I want to be very clear about that. The internet is the connection between the computers, and it powers the World Wide Web. But the World Wide Web is just one of many services that runs on top of the internet. There's email as well. There's a lot of other things. File sharing goes through the internet. Some voice calling apps now, or texting apps, will use the internet as well. So not necessarily just the web, although when it sort of first came out and most people were adopting it, the web is sort of the primary way that we interface with it on a daily basis, in a very visual way that we interface with it. So we'll start here, a little bit of history for the internet. So why is the internet around? Or just why is the internet? It's derived from this original thing called ARPANET, which stood for Advanced Research Projects Agency Network. And that actually came out of the Department of Defense back in the end of the 60s and early 70s, so very old. And the initial purpose for that was government researchers to share research and computing power. Because if you think about it, back in the day, a lot of governmental institutions, universities were a big one, a lot of them had their own sort of not really a supercomputer, in some cases supercomputer, but like really powerful computing device. And this was all so new at the time that these devices costed hundreds of thousands of dollars. And so not everyone just had them. But they were really crucial for crunching numbers for research. So the idea was, okay, like in this example here, we'll talk about this a little bit more in a second, but we can see Utah. So this is University of Utah. They have what's called a PDB-10, which is one of these original sort of mainframe computers, they called them. And so if I'm off somewhere else and I want to do some calculations, maybe I need a PDB-10. Maybe I'm at UC Santa Barbara here. So the point was, okay, I can connect to the one in Utah, even though I'm not physically there, and run my calculations on that. Because before, if you didn't have one near you geographically, you're out of luck. You couldn't do it remotely. And so ARPANET, the first successful connection happened between UCLA and Stanford, which you can see here, UCLA and SRI, Stanford Research Institute. And that happened on, can't remember the exact date now, but that was the first precursor to everything. So originally, this is actually a little later now, December of 1969. Even before that, it was just these two talking to each other. And that connection there was the first sort of connection ever made in what transformed later into the internet. And so over time, the network of research institutions grew as more and more people wanted to get online. So, on the East Coast, now people are interested, I want to share research with Stanford. I want to talk to those guys. And so keep in mind, this is December 1969. In May of 1973, just not even 4 years later, this is what the ARPANET looked like. And now we can see a lot of different places. We still have the original Utah. We have Stanford Research Institute. Let's see, USC, I'm sure. Yeah, UC Santa Barbara's in here, UCLA. But then there's a lot more on it too. And you'll see a lot of these numbers, what they mean is like PDP-10. These were all the machines that they had at the time, the IBM 1800. These were physical machines, and this is a network of literally every major machine connected to the network that you could use at any of these institutes. But as that got larger and larger, people outside of just researchers were really interested in using it. And people realized that the power of the internet would sort of grow if more and more people got on. But it was very difficult at the time because you needed a direct connection to these institutes. It cost a lot of money. There's a lot of red tape to even get on in the first place. So eventually, so many people wanted to use it, the force built up enough that in 1983, the switch literally happens between ARPANET and now what we call the current internet. And they actually, that day, January 1st, 1983, they switched protocols, which we'll talk about in a bit, and switched from this old sort of ARPANET where it's very controlled and not everyone could use it, to the internet where now suddenly anyone can get on that wants to. And so now we'll go into some key characteristics of the internet. And these are sort of founding principles of it that differed a little bit from ARPANET in a few ways. But let's look at these. So these are some key tenets. Decentralized. Does anyone know what this means? Can someone give me a working definition of decentralization? Yeah.
There's no one central hub where everything goes through.
Yeah.
It's computer to computer anywhere.
Great, yes. No one central hub where something has to go through. I will caveat that with there are actually, in the practical implementation of the internet, there are central hubs that you have to go through, but that's the right idea where there is not a single central governing body. No one can say, okay, now the internet's shut down for everyone, right? And so all the computers are talking to each other. And another one, public, right? This was the issue with ARPANET. It wasn't as public as people wanted it to be, so that was a change that they made there. And this other one that I added in, fault tolerant. And that just means if one part of the system goes down, the rest should keep working, right? If the internet goes out on Duke's campus, I don't want it to stop working here, right? That they should be totally independent systems. The worst being that I can't access some computer at Duke now that maybe I was connected to before. And so if you know what this map is, don't say it. I'm curious what people think this is who have never seen this map before, maybe don't have much of an idea what this is. Just guessing. What does this look like to you? What do you think this represents? It represents something physical in our world. Yeah.
Like underwater cables?
Yeah, that's right. So this is a diagram. I don't know. This might be a little old now. They're constantly, changing things up. But this is literally a network of physical cables that connect every continent in the world to each other so that the internet works. So that if I want to talk to a computer in Australia, oh, nice, I have a little one that wraps around the globe here and goes down there to Sydney, probably. Or if I want to talk to a computer in China, right, there's a connection. Or if there's not a direct connection, I can maybe go to Africa, and then Africa has another connection out to India. So something like that. But these are literal physical connections, and that's something I want to emphasize, right? We're so used to sort of this wireless age where we don't need, we have Wi-Fi, we have cell. We don't really think about what happens once we make the request past that. But in reality, a lot of stuff is still physically backed by cables that the data has to travel through. And you might say, oh, but there's satellites too, right? How much of the data goes through there? Does anyone want to throw out a number. What percentage, this surprised me a lot when I first heard it, but what percentage of internet do you think actually goes through satellites versus the undersea cables? It's a whole number, yeah. 5%? Anybody who thinks it's higher than 5%? Raise your hand. And who thinks it's lower than 5%? Raise your hand. Okay, interesting. Yeah, the lowers have it. Actually, only 1% of the internet traffic globally gets routed through satellites. So 99% of your stuff, if you go visit some server in Europe, it's going underwater here, right? And at some point, it will have gone through one of these lines. And actually, I won't click on this now, but this is an interesting article if you want to refer back to it. But this was in 2008. Literally, an internet cable, I believe, around northern Africa there got cut accidentally. And it literally knocked out 70% of sort of the bandwidth of all the network activity to Africa for that day. And everyone got really congested. You couldn't send stuff to another continent very easily. It just all slowed down because the remaining cables that were there had to take on the load. And so stuff had to wait in line, whereas before it could just go through that cable. So there's very real world ramifications to this stuff. And you'll see, sometimes bad actors will also try and purposely sever these cables because they're actually just so important, but an interesting aside there. So yeah, let's start, let's just go back to basics here. To think about networking, I think this is really helpful. Ajay mentioned that you sort of visited this in your, was it computer science principles class?
Yes, so I think if you had a chance to take the AP computer science principles class, I think they do briefly talk about this, but it's surprising because it's the only class actually that really, because AP Computer Science A doesn't talk about it, and at UNC also only like Comp 431, which we'll get to, really talks about this. So it's
it's important to not discuss. I also took computer science principles, and we did not talk about this. So hopefully, this will be a solid building block for building up. So. When we say computers are connected, how do they actually talk to each other, right? We have a cable running between them, but what actually happens over that cable? Fundamentally, computers can only send a 1 or a 0 to the other computer at once. So if you think of fiber optic is really common now, right? That's just a cable that carries light. And so a 1 or a 0 at its most fundamental is either the light is on or the light is off. It's a 1 or a 0. But that's really, actually, when you dig down to it, that's the most you can send over a wire at once. It literally is binary. And so how do we know how to interpret this data, right? And in other words, if we started receiving random 1s and 0s, how would you know what it meant? If I just started saying 1 0 1 1 1 0 0 right now, what does that mean, right? I gave it some sort of meaning, but you have no way of actually knowing what I meant, right? Maybe it was English characters, maybe it was something else. Without defining something beforehand, we have no idea. And you can think of this even at a very general level, like language. When I'm talking to someone, if they don't know the language that I'm speaking, there's no way for us to communicate really there, right? So there needs to be some sort of commonality there. And so like I said, no way of doing this without a predefined format. So we need to, before we start talking, agree on some way of interpreting this data. And so this is what we call a protocol. And this is fundamentally what underpins all of networking and the internet, is these standardized ways for computers to talk to each other. Because what you should think about is when you're thinking of network computers, just think, okay, they're just sending bits of data back and forth, a 1 at a time or a 0 at a time. They're just doing it really fast, but that's really all it is. And so from that, we now have to build up, we have to say, okay, maybe we predefined, 8 1s means an A, and then 7 1s and a 0 means a B, something like that, but some sort of predefined way of communicating. And so, cool. So as a little bit of a thought exercise, let's make a simple protocol to just send English letters. And on top of that, you can come up with your own here, but can you think of one that already exists for doing that with just 1s and 0s? Does anyone have an idea for? I heard from you. I want to see if someone else might have an idea here. And don't be afraid to get this wrong. Yeah, in the back. Yes, great. For those who didn't hear that, Morse code. So Morse code, in case you haven't heard of it before, predates sort of computers by a long time. But the idea was in the old days when telephone lines were just getting installed to communicate over long distances, all they could send, right, was an electrical signal that was either on or off, is 1 or 0. And so this guy named Morse came up with this code that used basically dots and dashes, or like a short beep and a long beep, to encode ones and zeros, or he didn't think of it as ones and zeros, but effectively it's ones and zeros, and then each one mapped to a different letter. So like a triple dot maps to, I think, S, something like that. And so that was at its most basic, just a way to easily transmit English over a wire. But as we know with the internet, it's a lot more complicated than that, right? We're not just sending text, we're sending other bits of data. We're sending raw data for like images. We're sending files over. There's a lot that we can send. So we need something a bit more widely applicable than just Morse code. And so what other protocols exist for this purpose, right? There's a lot that are predefined. And this is actually going to be your group activity today. I want you guys to get into groups and look up what other network protocols exist, what are they for, and submit this in the grade scope assignment here. So talk to your neighbors around you, try and find one that you think is interesting, and then just outline that in grade scope. Cool, guys. Let's try and bring it back here. Yeah, good things. I heard whisperings of many different protocols there. Before we move on, let's talk about some of them. Well, I didn't want to expose that yet, but so does anyone want to volunteer the protocols they found? Maybe something a little weirder, something that you don't think about every day? Yeah, in the back. SMTP, what is that?
Simple Mail Transfer Protocol.
Cool, and what service is that used for that we use a lot? Do you know? Simple mail, what do you think a mail transfer protocol might be used for? Yes, emails, nice. Yes, so emails, we don't think about this a lot, right? Because we go on gmail.com, outlook.com, it's all just through the website. But actually, email is so old that back in the day, it still uses its own protocol under the hood called SMTP, Simple Mail Transfer Protocol, I think that was it. And that is how, if you actually want to send an email to someone's email server, right, that's how they still communicate over this special protocol. So yeah, a great one there. Anybody else have a cool one that they found? Yeah. SSH, yes, that is a great one. I'm glad you said that. So SSH, do you want to say what that stands for?
Secure shell. I don't know the answer.
Yeah, no, that's good. Secure shell. Yeah, it's a weird one where the SH is part of shell. I don't know why they chose that. I guess SS was weird. So yeah, secure shell. And this one is interesting, right? Most protocols end in P, right? HTTP, SMTP. SSH, we don't necessarily think of as a protocol, and we'll actually get into here. But it is just a protocol. It also, predates sort of the World Wide Web by a while. And secure shell, what it lets you do is just connect, right? We were using the command line earlier, but maybe if I wanted to use the command line on a different computer on the network, I SSH in and then I get a command line on that computer. So that's what that's used for. Anybody else? So let's try and get one last one here that's maybe a little off the beaten path. Yeah.
IPFS, it's like interplanetary file system.
Yes, IPFS. That's a good one. That's a very a newer one, I think, right? So interplanetary file system. Do you want to explain what that is?
So what it says is like it's a newer version compared to the HTTP and HTTPS, and it is more decentralized and like has a similar characteristics to torrent and blockchain.
Yeah, good call. Okay, a lot of technical jargon there, but yeah, IPFS, basically a new idea to sort of replace HTTP and HTTPS. Hasn't caught on as much, I think, as the creators would have wanted, but yeah, that's the idea. It sort of serves the same purposes there, just in a different way that makes it a bit more decentralized. Yeah, cool stuff. Awesome. Well, I'm glad you guys said all that. Here's some protocols that we put up here, just because they're so common and pretty useful to know, no matter what line of work you're in, or even just research, right? So HTTP, and I put a little S there. There's original hypertext transfer protocol, which is what HTTP stands for. Then there's the secure variant, which is what everything actually uses now. If you go to a website, you'll see it's HTTPS. And the original purpose for this was serving web pages, or more specifically serving HTML, which stands for Hypertext Markup Language, so you can see the HT in common. But it actually became so ubiquitous that it's been sort of hijacked. It's used for a lot more than hypertext now because it's just so easy. Like, it's so easy to start an HTTP server and run one that people just send whatever data they want over it. There's SMTP as well, which was mentioned for email. FTP, File Transfer Protocol. SSH, I'm glad that was mentioned. Secure Shell, parentheses protocol, doesn't say it, but it is a protocol. And then we get to these two down here did anyone see these when you were looking these up, just by raise of hands? TCP and IP. Okay, good. Yeah, and so these are interesting protocols. TCP stands for Transmission Control Protocol, and IP stands for Internet Protocol. IP you've probably seen a lot of places, like your IP address, things like that. TCP maybe not as much. But what's interesting here is when you read these things, their use fundamentally is for routing internet traffic, routing network traffic, and for sending it back and forth. But if we just think of these all as protocols, there's some clash. There's like, okay, so if I'm sending stuff over IP, how do I use HTTP over IP, right? Like if I'm using IP to communicate with the computer, because that's what it does, it gives you like an IP address for a computer, how am I using these other protocols at the same time? How do they mesh together? And so that is where this comes in. And this is a really key graphic. If there's anything that you take away from today, I want you guys to really look at this. And this is it's called, so there's two main models of networking. There's the OSI model, and then there's this one called the TCPIP model. And this one is it's more simple compared to the OSI model. And it's fundamentally sort of what's been adopted. OSI is a bit more theoretical. This is what is actually like sort of happening every day on your computers. And so we'll see, the point of this is that we divided the entire sort of idea of network communication into 4 distinct stacks. And in each stack, there live different sort of protocols, right? Each stack has its own protocols for its purposes. And so the network access layer, we see Ethernet, right? Ethernet, in case you don't know what Ethernet is, that is just like if you ever plug in a computer to the internet, that's an Ethernet connection. And they omitted it here, I don't know why, but Wi-Fi too, right? And technically it's called 802.11, this is 802.3. That's another network access layer protocol. And then right above that, we get the internet layer. And this is where, there's a few different ones here, but key thing here I want you to look at, IP exists in this layer of network communication. And then right above that, we get these things called TCP and UDP. So TCP is sort of the older one, the more commonly used one. UDP is making a rise now, but for today we're just going to dial in on TCP, stands for Transmission Control Protocol. And then above that, we get this application layer, which is where we find a lot of the protocols that we just discussed, right? HTTP, SMTP, SSH is in here as well. All the ones IPFS, I think, unless it's not based on TCPIP, but I think it is. So yeah, and so when you start to think of it through this lens, now you can see how these protocols start to interact with each other. And the key idea here is that each layer should only have to worry about the data in its layer. And in other words, it should encapsulate the data of layers above it and not worry about that. So if I make an HTTP request, right, it has to be routed down the thing. Basically, I start up here, I make some sort of request, right, and then it goes down the stack. And at each level, that protocol actually handles the data above it. So I make an HTTP request. What's happening when you go to a website, you type in google.com, right? An HTTP request is made. And then a TCP request happens below it. And so what TCP does is it effectively takes the HTTP request. It doesn't touch it, but it wraps it up in sort of its own thing, adds its own data on, and then passes it down to the internet layer. And now IP takes over. IP takes it, wraps it up in its own thing. It doesn't touch the data in TCP. That's for TCP to deal with when it comes back. Wraps it up, adds its own thing on, and sends it further. Same with the network access layer. It doesn't care what happened above it. It wraps it up, adds on some data, passes it forward. And so that's the key idea, is that each layer is totally separate, right? And the idea is, oh, maybe like I do HTTP, TCP, but I want to use a different protocol for whatever reason at the internet layer. That's totally fine. I can use ARP. And then, I want to use a different network access layer. Instead of Ethernet, I want Wi-Fi. It doesn't matter because it just deals with its own layer and wraps it up there, makes it work for that single layer. It doesn't care what's above it or what's below it. And so going into that, we're going to focus on TCP/IP. And so we'll come back here, right? This is called the TCP/IP stack because these are the most commonly sort of used parts of each layer. And so we'll be dialing in on TCP and IP. Doesn't matter the network access layer, Ethernet or Wi-Fi are the common ones. And the application layer doesn't matter for now too. We're just going to look at this. Oh yeah, does anyone, sorry, thank you for the reminder, Ajay. Any questions about that? Sorry, I know that was a lot. Is it clear that each layer, let me condense it down to some key points. Each layer is totally separate from the layers before it. It doesn't matter what comes after it, doesn't matter what comes before it. It just worries about its own data. And they're And then that allows protocols to build on top of each other. So HTTP doesn't care if it's over TCP or UDP, right? It just cares that it gets sent to where it needs to go. Is that clear? Is there any sort of further distinction that you'd like there, in any place where it's a little fuzzy? Cool. So if I asked someone to explain what all the layers were to me right now, what their purposes were, do you think you could sort of give a general outline of it? If I thumbs up, thumbs middle, thumbs down. I won't ask anyone to, but let's see. Okay, seeing a lot of thumbs middles here. Is there a specific part that was unclear here, or yeah?
What's the role of the transport layer again?
Transport layer. Good question. Okay, so are we confused on what the purpose of each one is? Is that okay? Good. Okay, thank you for that question. Yeah. So the purpose is, okay, we'll get into this in a second, but maybe it'll be helpful to introduce it now, right? The idea is, if we go back to basics, so if we go to just, let's imagine just a single line between two places, right? And we're just sending ones or zeros over that. That's good, but the issue is now that line is totally reserved for me right now. No one else can use this line. And especially if that line is over really long distances, if that gets broken at any point, now that my whole series of communication has been cut off. So what we really want, and what the internet allows, right, is there's so many different nodes that there's a lot of different paths to get to the same place, right? I can drive from here back home to Greensboro on a whole bunch of different roads. And if one gets washed out, then it's fine, I can take another one. And so that's the idea here. TCP specifically, the point of this layer is to essentially chunk up the data before it into small things that we call packets. And what these packets allow us to do is, I'll introduce the analogy of just like the US Postal Service right now, right? So when we mail something off, maybe we have, we want to write someone a message, right? And so we write someone a message, and that'll be our application layer. We write a letter to someone. And then we want to transport it. So in this case, our letter is small enough that we can just put it into sort of just one envelope. But if we wrote someone, let's say like a 10-page letter, right, we might have to send it as two separate envelopes. So that's what the TCP layer does. And then past that, it separates our data, our letters here, into sort of bite-sized packets that can then be ingested later down. That like just a letter, right? And so then the internet layer, what this acts as is the address. So this is, I address my letter, I put where I want it to go, and I send it to here. And then the network layer is the actual handling of that. That's sort of the one layer below that's taking it and physically moving the letter. And so that's what each step is sort of a different layer of that process. But you can think of the internet layer as being the address layer, almost in a way. We say exactly where we want it to go. We can think of the transport layer as sort of the packing layer of packaging it up into nice, easy to transport sort of packets that we call them. The application layer is just whatever we want to send. And then the network layer is the physical moving of those packages. So sorry, I hope that clears it up somewhat. How's everybody feel after that? Thumbs up, thumbs middle, thumbs down. Is that a bit better on? Okay, cool. I'm glad, yeah. Thank you for that question. Great question. And yeah, I think that is a lot to digest. Before we dive into the next bit here, let's take a quick little 5-minute break or something. You can get up, get water if you need. I need water, so I will do that. But yeah, take a look at this, try and really understand it. If any other questions come up, feel free to let me know. Grab me or Ajay, and yeah, we'll talk about it. All right, cool. So I think everyone should be back here. If anyone knows anyone's, I see one person missing. Well, okay, we'll just do a little rehash then of what this is here. So yeah, so I hope you had some time to sit with that. Hope it sunk in a little. But yeah, just to rehash and go back over that. Just totally ignore this section for now. Just look at these 4 layers and just think of it as the application layer is my written letter. The transport layer is putting it in the envelope. The internet layer is addressing it, and the network access layer is physically moving that envelope through the system. And that's really all this is. And the protocols is just a lot of stuff that you can use for each layer, but don't get lost in that. If that's too much right now, don't even think about it. We'll get into that later. Cool. So with that, let's do a little bit of deep dive into IP, the Internet Protocol, and how we use it for the web. So the stack, remember that entire stack, the 4 layers there, it's called the TCPIP stack. It requires an requires an address and a port. And so this is where we split actually between TCP/IP, and actually these are sort of backwards because we have an IP address and a TCP port. So an IP address is just a 32-bit number, and if you've ever looked up, you can go on Google right now and look up what is my IP address, right? And you actually might get something that looks a little different from this, but you get this. This was one when I looked it up earlier. That's my IP address: 152.23.61.188. And the format, this specific format, is called IPv4, right? IP version 4, and it is a 32-bit number where each chunk is a number between 0 and 255. And so you can see, you can think of all the possible combinations there. That comes out to roughly 4 billion unique combinations with a 32-bit number. And so I want to ask this question, could that be a problem? Does anyone foresee this being a problem? And what is the problem? Yeah, Vincent.
Population will eventually reach that number.
Yeah, the population will eventually reach that number. In fact, we've almost doubled that number at this point, right? And so if you think about this, every person in the world with an iPhone, right, or not necessarily an iPhone, but some sort of phone, or people with double devices, right? Not everyone has a device, but in my daily use, I use a laptop and a phone. That's 2 devices right there. If we hooked everyone up to the internet directly, we'd very quickly surpass this 4 billion number, right? And so this is a problem. It's a very big problem. And so there's this new standard called IPv6, which is actually, instead of 32-bit number, it's a 128-bit number, which allows for so many devices to exist that there will never, I don't think there's some sort of thing, it's like there's not even that many atoms in the universe or something. It's an insanely high number. We're never going to reach that limit. But this was designed back in the 70s when they were no one's ever going to have 4 billion devices on a planet, right? Well, they were wrong. So right now, and there's some temporary patches we've come up with because if we were directly hooked into the internet right now, it wouldn't work. There's already more than 4 billion devices. There's some things we won't dive into here, but it's called network address translation that basically lets you to a server, basically everyone at this school looks like they're just coming from one IP address, if that makes sense. And then when you send something off to that server, it comes back, and then the network here on campus figures out who you are and sends it back to you. It's a lot more complicated than that. But that's how we've temporarily put a Band-Aid on the situation. Even then, we're still running out of IPv4 addresses, so we will be pivoting to IPv6 in the future, where it's sort of already coming. It's already upon us a little bit. But that's a little aside about addresses. Right now, just think IP address, 4 numbers separated by dots, just like that. And now we have what's called the TCP port. And this is a number between 0 and 65535, which is 2 to the 16th minus 1. This was another thing when they designed it, they're like, okay, we just need some sort of specification here. Let's do 2 to the 16th. And you'll often see, when you see IP addresses and ports, you'll see them together in this format, where we have the IP address first, a colon, the port that we want to access. And this is all we need to access anything on the TCP/IP stack, right? Remember the 4 layers there. It's called TCP/IP. It requires an IP and a TCP port. And through that, we can then address anything on our network. And this is an arbitrary port. I want to emphasize 25565. I think that's actually the Minecraft server port. I just chose a random one. But it can be anything. And so I want to ask another question here. Why is the port necessary if we already have an IP address, right? If I already know an address that I want to send something to, well, what's the point of the port? A little bit of extra data on the end. I've heard from both of you. I want to see if someone in this area want to take it, maybe. Just whatever you think, it doesn't, whatever comes to mind. Okay. Don't want to single anyone out. So who was raising their hands initially? I want to call on someone here. Yeah.
It's what part of the computer? If the IP is an address,
Mm-hmm.
this is send it to Hojo, what room?
Yes, a great example. That is the exact example I was going to use. But yes, thank you for bringing that up. So if the IP address is just a mailing address, that's not always enough. We need to sometimes say what room are we going to send the letter to, right? So where I live in So if I want something, I dox myself. I don't know why I did that. If I want to send mail there, I put that. Forget that. That's going to go on the internet now. So, but yeah, we need that because they just send it. It's not going to get to me necessarily. So let's move on from that. Forget that happened. Okay, so a deep dive into IP and web ports. So these ports are very important. Any protocol that operates at the application layer, which is just any protocol at the top layer, right? HTTP, SSH, HTTPS, it must have a port. And so you'll see that certain protocols typically have ports that they use. If I'm running an HTTP server on my computer, it will usually default to 80. If I'm running HTTPS, it defaults to 443. SSH 22, SMTP 25, 465, 587. And these are just these are predictable addresses, right? This is the idea that if I go to the White House and go to, I think, the West Wing, the president's going to be there, right? That's sort of just known. So when your browser actually goes to make an HTTP request, right, it by default will make an HTTP request on port 80 and HTTPS on 443. So Google servers, Amazon servers, they're listening for incoming requests on port 80 and 443 because that's what everyone agreed on beforehand. They're like, okay, if I need to make an HTTP request, I'll do it on these ports by default. That does not mean that they can't change, right? If I want to host an HTTP server on port 2222, I can do that. I just specify it in my code when I'm writing it. I say, okay, actually don't use port 80, use 2222. And the issue is now if someone else wants to access my server, well, they don't know that port. So they'll go to port 80 and then the computer will just be like, oh, there's nothing here. So good luck. But if they know port 2222 as well, right, and they address it like so in the web browser, that's how your web browser can do it too, they'll access my server. So yeah, much like addresses work in real life, the IP address is the dorm and the port is the specific root number. So a brief aside here about sort of the way that the networks work at a large scale. So very much like when we were mailing something off, very conveniently, we don't have to say exactly how to get our piece of mail somewhere, right? We just write an address on the envelope and trust that USPS, UPS, whoever is going to get it there. And that is very similar to how our routers work. When I want to access google.com, when I want to access apple.com, I don't have to say, okay, connect to this part, connect here, right? Because remember, we're traversing a very large network. There's so many computers connected. I'm going to actually have to make many different stops because my computer right now, it's only connected to the router. I don't have a direct connection to Apple servers. So it has to go through the router. The router, or our Wi-Fi access point, that's connected to the school's network. It has to connect somewhere up there. Then we have to go even further out, all the way until we get there. It'd be really annoying if I had to figure out how to do that sort of path because there's so many devices connected. It's just very inconvenient. So the way the internet works, we just say, okay, just get me there, and it'll sort of get there. The network will figure out how to get it there. And so that is done by special hardware that internet service providers have. The school has one. Anywhere they're hosting servers, they have them. And they're called routers, and they are machines specifically just meant to take in traffic and route it, right? Figure out the best path for it, send it somewhere else. Much like a mail distribution hub, right? I send my letter here, it goes off to some big hub, probably in Raleigh. That goes to some major Eastern Seaboard hub, and then that gets sent out to wherever I want it. And then this was mentioned earlier that this is not as key, so don't worry if this doesn't make too much sense, but the idea is that our data gets split into smaller chunks called packets. And the point of these packets is that they might take different paths but reach the same destination. So if I'm sending a ton of data, right, from me, maybe YouTube's sending me a ton of data. I'm watching a 4K YouTube video, that's a lot. So it's not guaranteed that at any point, maybe we're traversing through 10 different routers before it reaches me. We don't know that those are always going to be available, or that one might not get overwhelmed or fall off the network. So there's this idea of packets where that video gets chunked up into smaller bits and gets sent out. And if one of those packets, if one of these routers falls offline, the network's smart enough to figure out, okay, wait, we can go this way, we can go around it. And because it's small little bits of data called packets, it's okay if we lose one. There's actually there's protocols in place where I can request that packet to come through again. So losing one in transit isn't a big issue, and it lets you take many different routes to the same destination. They're both pluses, but they're distinct things. So it accounts for failures and just lets you have generally more options. And so just think of mailing separate packages, right? If I address 3 packages, I did this over the summer. I sent 3 letters home, and I sent them all on the same day, and they arrived weeks apart because they took some different routes. Ideally, in the internet, they don't arrive weeks apart, maybe milliseconds apart. But yeah, the idea is the same. And so I want to use this cool command here. It's called traceroute, and -p just signifies a port that you're trying to target. This exists on Mac. There is like an equivalent on Windows, but you have to install it. You don't even have to follow along if you don't want to, you can. But the idea here is just this command will actually tell us the route that we're taking to reach some sort of server that we give it. So if I do trace route, let's say I'll do port 22 because, actually no, I'll do port 80 because let's say we're doing web traffic, and let's say example.com. So I hit that, and you'll see it takes a second here. Let me expand this out so we can read it a little better here. Actually, I'll make it a little tinier because I want this all to be on one line for the most part. Okay, cool. So it's still going here, actually. But we can see that every single line here, that is a new server or router, in this case, that our internet just went through. So we started up here. We went through this one. This one actually has a name, very helpfully, but this is the actual address. This is, just look at what's in the parentheses here. So this is the router for this room. And then that got sent up to some higher thing at UNC. That got sent to another thing at UNC. Then that got sent to another thing at UNC Manning, then through Phillips, then through some other things here. These are not very descriptive names, not very helpful, but it gets relayed through all these routers. Oh, here's another .edu, probably something with UNC. And so you can see, just that one request has taken a ton of hops, and it's not even done yet, right? Normally this happens faster when you do it in your browser. But that's the point, is that you can see actually this is the route that it took, and if we drew it out, it looked like a weird little graph with a bunch of points that our internet traffic just took. So that's just a cool thing to see, I think. I actually didn't know about that until very recently. But you can see that that relay system works like that. It's not a single connection between you and the endpoint. It goes through a lot. And this is another little part. So with the web, this is also, not super, let me go slideshow mode. This is important, but it's not actually key to how it works. But there's this thing called DNS, which stands for Domain Name System. It is basically just a giant dictionary. So when you type in google.com, it gives you an IP address to actually connect to. Remember, an IP address is this, right? So it'd be very, very annoying if we had to memorize that for every site we ever wanted to go to. It's a lot easier for us to memorize a word, like something .com, right? .net. So DNS just allows us, when we type in google.com, this is actually the first thing that happens. Our computer looks up, okay, so what IP address, what number here should I address things to when I want to reach google.com? It's just like an address book. That's it. And there's another command here. This works on Windows and Mac. It's such a basic command that it's everywhere. But if I want to find the IP address of a service very easily, I can just ping it. So if I ping example.com, we'll see, there we go, it's pinging. And we get, I'll cancel that. But we can see example.com, that's its IP address right there. And that was achieved through DNS. It looked it up in the address book, it found this, and then sent the data there. You cannot send data to example.com on its own. You need an IP address. So does that make sense to everyone, how those systems play together so far? IP addresses, DNS. Can I get a thumbs up, thumbs middle, thumbs down? Cool. Awesome. So let's blow this back up. Okay, so now with all of that, with TCP, with IP, with DNS, we can figure out where we need to address our traffic, right? That's all the lower layers. If we come back to the layer diagram, there we go, right? TCP, we looked at that, that's the port. IP, we looked at that, that's the address. Network access layer, we didn't talk about that, but that's like Ethernet or Wi-Fi, right? Just take it on good authority that works, because that's very hardware related stuff, we won't get into that. So now we have everything we need to look at the application layer. So that's what we'll look at next. And that is where we get HTTP. So because we covered all this, we now can operate at a higher level. And HTTP is just one of many protocols. It's just a way that people have said, okay, this is how we're going to send websites to each other. We all agree on it. Because remember, if I'm just sending you random data, how do you know how to interpret it? I don't. So we said, okay, for websites, we're going to use this thing called HTTP. And HTTP is luckily high enough level that it's actually very easy to look at a full HTTP request and dig into it and see what this protocol actually mandates. So we'll go ahead and do that here. We'll click on this. If you want to follow that URL yourself, oh shoot, where'd that go? Yeah, it's just, if you look up curl online, it's probably going to be in the first few results, but it's recbin, request bin, or short for request, reqbin.com/curl. And this curl tool is actually one that you can install on your command line too, but I just wanted to use a web version here so you could follow along if you wanted to. Does everyone have that and wants that? Tell me if I need to go back now. Okay, cool. So we'll use the curl command, and what this lets us do is basically just make a very simple HTTP request to where we want to go. So I'm curling example.com, right? And this, if we break it down, example.com, that maps to an IP address. And if we even want to be very explicit, right, port 80, that's the HTTP port. And so the reason I don't have to type this every time is because our web browser and curl is smart enough to know, okay, if you're doing an HTTP request, the default port is 80. But if you want to be very specific, you can append it there like that. And then HTTP, just saying the protocol we're using. So let's go ahead and run that. And we get this nice thing back right here. And so I'm actually going to come over to raw, which shows us our entire raw HTTP request. And this is it. There's a lot to it, or there's a lot of lines to it, but there's actually not a ton of data to it. Let's just start at the top. So this is HTTP. This is how people said, okay, when you make an HTTP request, this is what the response is going to look like. And this is what every HTTP response is going to look like that you look at. If you made a request to a different site, you're going to get the same sort of thing that starts off with this. They say HTTP 1.1, 200 OK. And that just means 200 OK just means, OK, there's no error. Here's your stuff. And that can change. The number can change to signify different things. Who's seen a 404 error when they try and visit a website? Or a 500 something? That's what this is. That's where that comes in. And so when people made this, they said, OK, let's do it like this. Let's send the HTTP header with some sort of status number. And then let's have this next section called headers, which is just some sort of metadata, or data about our data. So we can see, I like this one, content length. It tells us how many characters is our response about to be. So we know how to do that. It gives us a helpful last modifier. When was the last time someone touched this page? What is the date right now? Content type tells us it's HTML, very useful. And these headers can actually change. Websites can choose which ones to send. There's some that you'll see specifically on Google that don't exist on others. But basically, they're just a way of telling your browser, telling whoever requests the data, here's some data about the data. Here's some extra information. And then the HTTP protocol says, OK, once you're done with your headers, add a blank line, and then just dump whatever data you might want to send the person. And so this right here, for anyone who's familiar with HTML, this is the entire code for the website, example.com. Oops. If we do this, this is literally the code that just makes this page. And it's all right here. And if we actually go to HTML, we can see a nice little preview. Yeah, there it is. But that's all HTTP is. So you can see it's actually a very high-level protocol. You can look at this for any request you want to make. If you ever get curious, hop in here, make a request to some website, see what it returns. But that's it. That is the application layer. So you can see how simple things are at that layer because everything's handled for us below, the addressing, the ports, all that stuff is taken care of. We just worry about the data to send. And we just said, OK, let's do it this format. We'll have HTTP at the top, we'll have our headers, and we'll have our data. And so now you know what HTTP is. That is literally what's happening whenever you load a website. Does anyone have any questions about that? Any comments? Cool. Does everyone feel comfortable if you had to make a curl request and understand what came back in the HTTP request? If you had to understand all of this right here, how do we feel about that? Good, middle, bad? Okay, seeing good for the most part. Cool. And this is just one of many protocols, and it's totally go ahead, play around with it. If you have the time, that's how you get familiar with these things. But yeah, that's that. So I'll hop into, yeah, and so this is, if you're really interested in networking and stuff, this is a very quick overview, very high level, right? There's a lot more that goes into these things at these levels, like what actually happens at the TCP level, the IP level. And so luckily, we have a class on that, Comp 431, Internet Services and Protocols. So if you are at all interested in that stuff, this will give you a great foundation. And then if you go into a lot of other classes that just use like higher level HTTP things like 423, you'll make use of these protocols at least a very high level. So you'll make requests to APIs and whatnot. So are there any questions in particular about everything we went over? The network stack from before, the IP, or yeah, IPs and the web, now HTTP in particular. Cool. I guess, yeah, there's not a ton more there. I did want to show one other thing. I didn't want to run out of time here, so I did gloss over it. Let me see here. Oh yeah, this is one thing. So this might have been more of a problem back in the day than it is now. But when you go to load a website now, you'll notice things are really quick, right? Because like I go to YouTube, load a video, it happens almost instantly if I'm on good Wi-Fi. And that's actually because you know, when I load in YouTube.com, they have literally put servers all over the world. They have a server in America. They have one, probably on every continent, probably in every like sub-region of every continent too, to very quickly serve things. Because if I go back to here, just want to emphasize, right? If they have one server in America and I'm requesting a video in like Japan, that's gonna take a while, right? It's gonna be very annoying to deal with. So there is this notion of sort of replicated data elsewhere, and that is a really interesting sort of problem that you encounter when you start dealing with systems of scale. Is like, okay, like how do we distribute this data? Because you're never gonna overcome this, right? These are sort of the physical limits of our world. And so if your data is far away, it's gonna take longer to access. And if I actually have, let's see, I have two servers here that we can just look at, right? This first one is just a New York City server. And so if I'm gonna ping it right here, because ping also has this wonderful other feature of telling us, if I cancel that, time. This tells us how long our request took. So this ping, just sending you a little bit of data, seeing what's up. The first one took 34 milliseconds and 23, 22, 28. So very quick, right? Remember, there's 1,000 milliseconds in a second, so it happens in a fraction of that time. If I go ahead and ping the Sydney server, right? This one exists physically in Australia. Look at that. It's taking almost 10 times more times, 327 milliseconds, 240, right? That's because literally, every one of these pings has just been routed up through the university, over through an underground or underwater cable, all the way to Australia. So it's just an interesting sort of thing to think about when you use the internet and see things load super fast. You keep in the back of your mind, that's probably near you, and when stuff takes a longer time to load, that might be further away. Maybe it's because you're on a bad connection. But just sort of keep in mind those things, that the internet is a very physical thing, right? We don't think of it as physical very often, but it is. It's constrained by sort of the rules of our physical world, and yeah, connected by that. So thank you guys. I think, yeah. And with that, I will bring it over to assignment 8. Not totally done yet. It will be out by tonight. I promise it will be by tonight, so you'll have a full week to work on it. It'll be due next, our typical 1 week due date, 5 a.m. So yeah, thank you all for that, and yeah, have a good day.